In 1981, an astronomer working with a small team of colleagues pointed a telescope at a patch of sky near the constellation Bo-Otes and began counting galaxies. He expected the familiar pattern, a slow scatter of faint points thinning out with distance, the ordinary texture of the universe. Instead, at a certain distance, the galaxies simply stopped. Not a few fewer than expected, almost none at all. This is why astronomers who study the large-scale structure of the cosmos still return to this one patch of sky, because what looks like an empty gap in an old survey turned out to be one of the strangest and largest structures ever confirmed to exist. A region of space so vast and so hollow that it forced scientists to rethink what the universe is actually made of. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath and let's begin. To understand why a patch of empty sky could unsettle an entire field of science, you have to understand how astronomers build maps of the universe in the first place. We cannot travel to other galaxies. We cannot send a probe far enough to check whether a distant cluster is really there. Everything we know about the shape of the universe on the largest scales comes from a single trick of light called redshift. Space itself is expanding, and as it expands, the light traveling through it gets stretched along with it. A wave of light that left a galaxy as blue light can arrive at our telescopes stretched toward the red end of the spectrum. And the amount of that stretching tells us how far the light has traveled, and therefore, how far away the galaxy sits. Line up enough of these measurements and you get something like a three-dimensional map, built not from photographs but from the color of ancient starlight. The team that first noticed the gap near Bo-Otes was running exactly this kind of survey. They chose a few narrow slices of sky, thin columns reaching outward from Earth like drinking straws pointed at the stars, and they measured the redshift of every galaxy bright enough to catch in each one. If the universe were filled evenly, the way early cosmologists once assumed it must be, each column should have shown galaxies scattered at every distance, thinning gradually the farther out you looked, but never disappearing entirely. That is not what the data showed. At a certain distance, in more than one direction, the galaxies vanished almost completely, and then resumed further out, as if something had carved a clean gap directly through the survey. The immediate suspicion was error. Maybe the equipment had missed faint galaxies. Maybe the survey fields were too narrow and had simply gotten lucky, slicing through the edges of ordinary small voids and exaggerating them into something that looked enormous. The only way to settle the question was to go back and do the survey properly, expanding the search into the space between the original narrow columns and measuring far more galaxies across a much wider stretch of sky. That follow-up survey took years to complete. When the results finally came in, the astronomers asked a simple question of the data. In the distance range where the gap had appeared, how many galaxies should a normal patch of universe contain? The honest answer, based on everything known about the density of galaxies elsewhere, was that dozens should have shown up in the sample. What they found instead was close to nothing. The gap was real. What had been dismissed as a possible glitch in a modest 1981 survey turned out to be a genuine hole in the structure of the universe. And once astronomers confirmed it, they had to measure exactly how big that hole actually was. The numbers, once astronomers worked them out, were difficult to hold in the mind. The void sits roughly 700 million light-years from Earth, in the direction of the constellation that gave it its name. Its interior stretches across a diameter of roughly 400 million light-years, which means its radius alone is about 200 million light-years, a distance that light itself needs 200 million years to cross. Picture a bubble that size, sitting in otherwise ordinary space, and try to imagine what ordinary space should have put inside it. A region of the universe this large, filled at the average cosmic density, would normally contain somewhere in the range of 2,000 galaxies, entire islands of stars, each one containing hundreds of billions of suns, each one a universe of its own, by any human standard of scale. The actual count of galaxies confirmed inside the void is around 60, not 2,000, 60. A volume large enough to be measured in millions of cubic megaparsecs, accounting for a noticeable fraction of the observable universe, and it holds barely a few dozen galaxies where thousands were expected. One astronomer, who spent years studying the region, offered a way to feel the scale of it rather than just read the number. If our own galaxy happened to sit at the center of this void, he pointed out, we would have had no way of knowing that other galaxies existed until well into the 20th century, because the nearest ones would have been too far away and too faint to detect with the instruments available at the time. We only learned that the Milky Way was one galaxy among countless others in the 1920s, when a separate patch of light in the sky, long assumed to be a nearby cloud of gas, was shown instead to be an entirely separate galaxy, sitting far beyond the edge of our own. That discovery is what convinced humanity that the universe was bigger than one galaxy in the first place. Inside the void near Boötes, an observer would have had to wait decades longer for that same realization, simply because there would have been almost nothing nearby to reveal it. It is worth being precise about what the word void actually means here, because it does not mean nothing. Space inside the region is not a true vacuum in the philosophical sense. Hydrogen atoms still drift through it. Dark matter, whatever it ultimately turns out to be, is still present in some amount. The faint background glow left over from the early universe still passes through every cubic meter of it, exactly as it does everywhere else in the cosmos. There is no wall marking its edge, no membrane holding it apart from the rest of space. What is missing is concentration, the matter that should have clumped together under gravity, forming stars, forming galaxies, forming the vast, glittering structures we see everywhere else, never gathered here in anything like the normal amount. Current estimates put the density of matter inside the void at somewhere between a sixth and a third of the average density found elsewhere in the universe. Whatever process usually pulls hydrogen gas together into galaxies simply failed to do its usual work across this stretch of space, or did it so weakly that almost nothing came of it. That is the detail that keeps researchers coming back to this region decades later. It is not just an absence. It is a failure of the ordinary process of galaxy formation, playing out across a region of space large enough to make the failure impossible to ignore. The 60 or so galaxies that do exist inside the void are not scattered randomly through its volume, and that turned out to be one of the most telling clues about how a hole this size could have formed at all. When astronomers mapped their positions carefully, using radio observations of neutral hydrogen gas, they found the galaxies clustered together in small groups and loose pairs, arranged along something like a narrow thread running through the middle of the void rather than spread evenly across its interior. That thread, a rough cylinder of galaxies threading through an otherwise empty sphere, became the key piece of evidence for how the void most likely grew to such an enormous size. The leading explanation is that the Boötes void did not begin as a single vast hollow carved out of the early universe all at once. It began instead as several smaller underdense regions, each one modest by cosmic standards, each one slowly losing whatever matter it contained as gravity pulled that matter toward the denser walls surrounding it. Over billions of years, those smaller regions expanded, the way all underdense regions in the universe tend to expand, since less mass means less gravity holding the interior in place, which means the material inside drains outward toward the surrounding walls, faster than new material can gather to replace it. As the smaller voids grew, their edges eventually touched and then merged. The way soap bubbles pressed together will eventually pop the thin wall between them and become one larger bubble. The thin filament of galaxies running through the center of the void is thought to be a remnant of exactly that kind of merger. A leftover boundary marking where several smaller empty regions used to meet before they became one enormous one. If this picture is correct, the void near Boötes is not some singular anomaly that defies the normal rules of cosmic structure. It is instead an unusually large but fundamentally ordinary product of a process that happens throughout the universe constantly, just carried further and given more time than almost anywhere else we have been able to observe in detail. That explanation fits comfortably within the standard model cosmologists use to describe how the universe evolved from a nearly smooth early state into the clumped, structured cosmos we see today. Tiny variations in density, present from the very earliest moments after the Big Bang, are thought to have been the seeds of everything that followed. Regions that started out slightly denser than average pulled in more matter through gravity, growing over billions of years into the galaxies, clusters, and vast filaments that fill the sky. Regions that started out slightly less dense fell behind in that same competition and grew instead into voids, some modest, a few, like this one, extraordinary. Detailed computer simulations of cosmic evolution, built to match the density variations recorded in the leftover glow of the early universe, do produce voids of comparable size, given enough time, which is part of why most researchers consider the Boötes void consistent with the standard picture rather than a sign that something in it is broken. And yet, consistency is not the same as full explanation. The simulations can show that voids this size are possible. They cannot tell you, in advance, why this particular patch of sky, out of the entire observable universe, happened to be the one where the conditions lined up to produce a hollow region on this exact scale. That gap between what the models allow and what they can actually predict is one of the reasons the void continues to draw attention from researchers who study the shape of the universe, 4 decades after it was first suspected to exist. For most of the last century, when scientists pictured the structure of the universe, they pictured galaxies first and emptiness second. The bright things, the stars, the glowing disks and swirling arms, were treated as the subject, and the dark space between them was treated as background, a canvas rather than a character in the story. The discovery of enormous voids, like the one near Boötes, helped flip that picture on its head, and the more carefully astronomers have mapped the sky since then, the more thoroughly that reversal has held up. By most careful estimates, voids account for somewhere around 80% of the entire volume of the observable universe. The galaxies, the filaments, the great walls of light that show up so vividly in every map of the cosmic web occupy only a small sliver of the actual space out there. Matter has not filled the universe evenly. It has gathered onto thin surfaces, sheets and threads stretched across the boundaries between enormous hollow regions, the way a soap film stretches across the edges where bubbles meet. The galaxies are not the structure of the universe, so much as they are the residue left clinging to the surface of something far larger and far emptier. Voids come in a wide range of sizes. Small ones, tens of millions of light-years across, are common throughout the cosmic web, tucked between filaments almost everywhere you look. Larger ones stretch for hundreds of millions of light-years, with the void near Boötes standing among the largest that have ever been mapped in careful detail. And there are hints, still debated, of structures larger still, regions of underdensity so vast that confirming them fully will take future generations of surveys. The size an individual void can reach depends on how much time it has had to grow and how underdense its starting conditions happen to be. And voids do keep growing. As the universe expands, whatever matter remains inside, a void continues to drain outward, pulled by the gravity of the denser walls surrounding it, the way air continues to leave a nearly empty balloon. The walls grow a little denser. The void grows a little emptier. Given enough time, this process only sharpens the contrast between the crowded filaments and the hollow spaces between them. The void near Boötes is not a fixed, finished object. It is still in the middle of this slow process, still growing, still losing whatever galaxies remain along its central filament to the pull of the walls at its edges. Given another few billion years, it will very likely be larger and emptier than it is today. We do not live inside this particular void. Our own galaxy sits at the edge of a much smaller, underdense region, sometimes called the local void, a relatively modest gap compared to the one near Boötes, with our own Milky Way perched near its boundary rather than buried at its center. Beyond that local emptiness lies a much richer, denser stretch of the cosmic web, filled with enormous gatherings of galaxies, pulling our entire region toward them across hundreds of millions of light years. But the question of just how typical or atypical our own position in the universe might be does not end there, and it leads to one of the most contested debates in modern cosmology. A group of researchers proposed, in a series of papers published over the last decade, that the modest local void surrounding our galaxy might actually be the near edge of something far bigger. Their argument was based on careful galaxy counts, extending outward from Earth across a much larger stretch of space than earlier surveys had covered. When they measured how many galaxies actually existed within roughly 1 billion light-years of us, in every direction, the total came out lower than the average density of the universe by something in the neighborhood of 1/5. If that measurement holds up, it suggests we are living not at the edge of a small local gap, but near the center of an underdense region so large it dwarfs even the one near Boötes, stretching across something on the order of 2 billion light-years. The proposal remains contested. Some later surveys have supported the finding. Others have measured a weaker effect, or questioned whether the original sample was biased in some subtle way. But if the larger void is real, the consequences reach far beyond a simple correction to a galaxy count. They touch one of the deepest open problems in cosmology, a disagreement that researchers have started calling the Hubble tension. Astronomers have two very different ways of measuring how quickly the universe is expanding. One method looks at the ancient light left over from shortly after the Big Bang, the faint glow that fills the entire sky and carries a record of the universe when it was still young. The other method looks at relatively nearby stars and galaxies, using their brightness and their redshift together to measure expansion directly in our own cosmic backyard. Both methods are extraordinarily precise. They do not agree. The nearby measurement consistently returns a faster expansion rate than the ancient one, by a margin small enough to sound trivial and large enough to have kept cosmologists arguing for the better part of 2 decades. If we happen to be sitting inside, or near the edge of, an enormous underdense region, that disagreement suddenly has a possible explanation. Matter inside, a void experiences an outward gravitational pull from the denser material surrounding it, since gravity always pulls toward wherever mass is concentrated, and a void is surrounded on all sides by exactly that kind of concentration. That outward pull would add extra velocity to galaxies near us, making our local corner of the universe appear to expand somewhat faster than the cosmos does when averaged across its entire volume. We would not be measuring the universe incorrectly in that scenario. We would be measuring it correctly, but only for the particular neighborhood we happen to occupy, a neighborhood that may not represent the average conditions found everywhere else. Whether this explanation fully accounts for the disagreement between the two expansion measurements, or only accounts for part of it, remains an open and actively debated question, with new papers on the subject appearing every year. What is not in dispute is the deeper implications sitting underneath the debate. Cosmology has long assumed that our location in the universe carries no special significance, that an observer anywhere else in the cosmos would see roughly the same picture we do. The discovery of enormous voids, confirmed by the region near Boötes, and possibly echoed by an even larger structure surrounding our own galaxy, complicates that assumption in a way the field has not yet fully resolved. There is a second, independent line of evidence that connects enormous voids to something even older than the galaxies themselves: the faint background radiation left over from the very early universe. Roughly 380,000 years after the Big Bang, the universe cooled enough for light to travel freely for the first time, and that ancient light still reaches us today, arriving from every direction, carrying a record of what conditions looked like at that early moment. Astronomers call it the cosmic microwave background, and its temperature is extraordinarily uniform across the sky, varying by only the tiniest fractions of a degree from one direction to another. Those tiny variations matter enormously because they map onto the seeds of structure that would later grow into galaxies, clusters, filaments, and voids. In the early 2000s, researchers combing through detailed maps of this background radiation found something unusual: a patch of sky that was noticeably colder than its surroundings, with no obvious galaxy cluster or known structure to explain why. Researchers began calling it simply the cold spot, and it became the subject of years of investigation. One of the leading explanations involves exactly the kind of structure we have been describing. If an enormous void sits between Earth and that patch of the ancient sky, light passing through the void on its way to us would lose a small amount of energy, because it would fall into the void's gravitational landscape on one side and climb back out on the other. And if the universe had expanded in the meantime, that climb out would cost slightly more energy than the fall, and provided this subtle effect, named after two physicists who first worked out the mathematics behind it, would show up as exactly the kind of cold patch astronomers found: a faint chill imprinted on ancient light by an enormous stretch of emptiness sitting somewhere along its path. Subsequent surveys aimed in that direction did turn up evidence of a large, underdense region, roughly where the effect would require one to be, sometimes described as one of the largest voids ever proposed, stretching across a truly staggering portion of the sky. Confirming the full picture has taken years of careful follow-up work, and some details remain debated, but the basic connection between enormous voids and measurable imprints on the oldest light in the universe is no longer a fringe idea. It is a real, tested phenomenon, and the void near Boötes gave researchers the confidence to take it seriously in the first place, because it proved that voids on this staggering scale could exist, could be mapped, and could be confirmed beyond reasonable doubt using ordinary observational methods. Once one enormous hollow region had been measured carefully enough to remove any doubt, the idea that ancient light might carry the fingerprints of similar structures elsewhere in the sky stopped sounding speculative and started sounding like a natural next step. It helps to understand what actually happens to space itself inside a region this empty, because the physics inside a void is genuinely different from the physics in a crowded cluster of galaxies. Even though the same laws apply everywhere, gravity is the weakest of the fundamental forces we know of, and it only becomes noticeable when enough mass gathers in one place to make its pull significant. Inside a dense cluster of galaxies, that pull is constant and strong, tugging everything inward, slowing the local rate at which space expands compared to the average for the universe as a whole. Inside a void, there is almost nothing to provide that inward pull. Mass is scarce, so gravity has very little to work with. Into that gap steps a different influence entirely: the mysterious pressure researchers call dark energy, the same effect responsible for the overall acceleration of the universe's expansion. Dark energy does not care how much matter is nearby. It acts everywhere, uniformly, pushing space to expand a little faster with every passing year. In a dense cluster, gravity fights back against that push, and mostly wins, at least locally, holding galaxies together, despite the overall expansion happening around them. Inside a void, gravity has almost nothing to fight with, so dark energy wins by default, and the interior of the void expands measurably faster than the crowded regions surrounding it. This creates a feedback loop that keeps building on itself. A void expands a little faster than average. That faster expansion spreads out whatever matter is left inside it even further, lowering the density even more. Lower density means even less gravity to resist the push of dark energy, which means the void expands faster still. Researchers have actually measured this effect directly by tracking how galaxies sitting near the boundary of underdense regions move compared to galaxies embedded deep inside crowded filaments. The galaxies at a void's edge consistently show extra outward motion, beyond what the overall expansion of the universe would predict on its own, motion that can only be explained by the combined pull of the denser material surrounding them and the reduced resistance of whatever thin material remains inside. It is a strange kind of arrangement to picture: an interior with barely enough gravity to notice, surrounded on every side by walls dense enough to keep tugging outward on anything left within reach. Over long enough stretches of cosmic time, the effect only becomes more pronounced, sharpening the divide between the hollow interior and the crowded boundary until what began as a mild underdensity becomes an unmistakable, enormous gap in the structure of the universe. This is part of why researchers describe voids like the one near Bo-Otes as more than a curiosity of galaxy counting. They function as natural laboratories, places where dark energy operates with almost no competition from gravity, giving scientists a chance to study its effects in relative isolation far more cleanly than is possible in the crowded, gravity-dominated regions where most of the visible universe happens to sit. Try, for a moment, to imagine what a journey through this region of space would actually look like. Start at the near edge of the void, at the last ordinary filament of galaxies before the emptiness begins. Behind you, the sky is crowded, filled with faint smudges of light, each one an entire galaxy containing hundreds of billions of stars, scattered across every direction you look. Cross the boundary, and that crowding begins to thin almost immediately. Within a relatively short distance, measured against the scale of the void as a whole, the familiar scattering of galactic light becomes sparse, then rare, then nearly absent. Traveling at the speed of light, it would take about 200 million years just to cross from the edge to the center, and in all that time, an observer looking outward would see almost nothing. No familiar spiral galaxies drifting past. No clusters glowing faintly in the distance. Only the same faint, uniform background of ancient radiation that fills every corner of the universe and every few tens of millions of years. Perhaps the distant, isolated glow of one of the 60 or so galaxies scattered along the central filament, sitting alone in a stretch of space large enough to swallow it without a trace. Continue on, and eventually, the emptiness would begin to thin again. The ordinary structure of the cosmic web resuming as you approach the far side, filaments and clusters slowly reappearing until the sky looked once more the way it had before you ever crossed into the void at all. From either side, the journey through this region would feel less like crossing a gap and more like crossing an ocean, a stretch of space so vast and so uniform that individual features would barely register against the sheer scale of what surrounded them. What makes this picture especially strange is that nothing marks the transition. There is no visible wall, no dramatic boundary, no sudden change in the laws of physics between the crowded region outside and the emptiness within. The void is simply less, everywhere, all at once, across a stretch of space, large enough that crossing it would take longer than the entire history of complex life has existed on Earth. And yet, despite that emptiness, the void is not a separate universe or a broken piece of one. The same gravity operates inside it. The same dark energy pushes on every cubic meter of it. The same background radiation, the leftover glow from the earliest moments after the Big Bang, fills its interior exactly as thoroughly as it fills the crowded regions on either side. What differs is only the accident of history, the particular way matter did or did not gather here billions of years ago, when the earliest seeds of structure were being planted across the infant universe. The merger explanation accounts for how a void this size could grow once it started forming. But it does not answer a harder question, which is why this particular patch of sky ended up as the site of one of the largest hollow regions ever measured, while neighboring patches of comparable size went on to become dense superclusters instead. Detailed computer simulations built to match the early universe can produce voids of this scale. They are not common in those simulations, but they are not impossible either, appearing as a natural, if rare, outcome of the same random density fluctuations that produced every other structure in the cosmos. The trouble is that a simulation showing something is statistically possible is not the same as a simulation explaining why it happened in one specific direction rather than another. Cosmologists can run their models 1,000 times and get a handful of voids this large scattered somewhere across the resulting universes. But they cannot point to the version of the universe we actually live in and say, in advance, that a void of exactly this size should appear here, in this constellation, at this distance, rather than in some entirely different patch of sky. That gap between statistical possibility and specific explanation is uncomfortable for a field that prides itself on precise prediction, and it is part of why the void near Bo-Otes has never quite settled into the category of solved problems. Every few years, a new paper re-examines its structure, refines the count of galaxies along its central filament, or tests whether its dimensions match slightly updated models of how density fluctuations should have behaved in the earliest fractions of a second after the Big Bang. None of these papers have overturned the basic picture. The void is real, it is enormous, and it most likely grew through the gradual merger of several smaller underdense regions. But the deeper why, the question of what exactly determined that this stretch of the early universe would tip toward emptiness rather than abundance, remains open in a way that few other confirmed cosmic structures can claim. There is something almost unsettling about a mystery that has survived this long without collapsing into either a full explanation or a disproof. Most scientific puzzles eventually resolve one way or the other. Either the strange result turns out to have a mundane cause, or the strange result forces a genuine revision of the underlying theory. The Bo-Otes void has done neither. It has simply persisted, confirmed beyond reasonable doubt, consistent with the standard model in its broad outline, and yet still missing a satisfying answer to the most basic question anyone asks when they first hear about it, which is simply, why is it there? The discovery of enormous voids has also raised a quieter question, one that reaches beyond cosmology into the search for life elsewhere in the universe. If regions this large can exist with only a scattering of galaxies inside them, what would it actually be like to evolve as a civilization inside one? And would that civilization even be able to figure out the true shape of the universe surrounding it? Galaxies need a reasonable supply of heavy elements to build rocky planets in the first place. Elements like carbon, oxygen, and iron that are forged inside stars and scattered outward when those stars eventually reach the ends of their lives. A galaxy that formed in relative isolation, with fewer neighboring galaxies to collide with, merge with, or trigger extra bursts of star formation, tends to build up those heavy elements more slowly over time. That could make void galaxies less generous nurseries for rocky worlds, at least early in their history, since the raw material for planets like Earth would have taken longer to accumulate. On the other hand, isolation carries its own advantages. Galaxies embedded in crowded clusters experience frequent close encounters, gravitational disruptions, and occasional violent mergers, any of which can scatter forming planets, strip gas away before stars finish assembling, or trigger bursts of intense radiation from actively feeding black holes at a cluster's core. A galaxy sitting alone in the middle of an enormous void experiences almost none of that turbulence. Its stars form at a steady, unhurried pace, undisturbed by neighbors, and any planets that do form around them would have long, quiet stretches of time to develop complex chemistry without the risk of a nearby catastrophic event interrupting the process. Whether that trade-off favors or disfavors, the emergence of life is not yet something science can answer with confidence. There is a second, stranger question buried inside the first one, which has to do with how a civilization inside a void would come to understand the universe at all. An observer living in a dense, crowded region of the cosmic web looks outward and sees galaxies in every direction, at every distance, providing an abundance of natural reference points for measuring how the universe is expanding and how its structure is arranged. An observer living deep inside a region like the one near Boötes would see almost nothing. Their night sky would be close to empty, with only the faint, isolated glow of a handful of distant galaxies to work with, and even those would sit along one narrow filament rather than scattered helpfully in every direction. Reconstructing the true scale and shape of the universe from so little data would be extraordinarily difficult, and it raises an uncomfortable possibility about our own situation. If our own galaxy sits near the edge of a large, underdense region, even a modest one compared to the void near Boötes, are our own measurements of cosmic expansion, our own sense of how crowded or empty the universe typically is, subtly shaped by the particular neighborhood we happen to occupy. That question does not have a settled answer yet, but it is one of the reasons researchers keep pushing surveys further outward, well beyond the boundaries of our own local neighborhood, hoping to confirm whether the picture we see from here matches what an observer would find almost anywhere else in the cosmos, or whether our view has been quietly filtered by the accident of where we happen to be standing. For most of the history of modern cosmology, scientists worked from a simplifying assumption, first written into the mathematics of an expanding universe in the early 20th century. The idea that matter is spread evenly through space and looks roughly the same in every direction once you average over a large enough volume. This assumption was never based on direct observation. It was based on convenience, because a universe that looked the same everywhere was far easier to describe mathematically than a universe filled with lumps, threads, and gaps. For decades, that assumption held up reasonably well, mostly because the instruments available could only map the relatively nearby universe in any detail, and at those more modest scales, the assumption of rough uniformity was not obviously wrong. As redshift surveys grew more ambitious through the final decades of the 20th century, a different picture began to emerge. One influential survey from the middle of that period produced a map showing more than 1,000 galaxies arranged not evenly across the sky, but gathered into long, thin sheets with enormous gaps stretching between them. The universe, once the resolution was good enough to see it clearly, looked less like an even mist of matter and more like a sponge, or a certain kind of dense foam, with the visible material clinging to thin walls and threads, while the interior of each cell in that foam remained close to empty. The void near Boötes stands as one of the clearest and most thoroughly measured examples of exactly this kind of cell, discovered even before the broader foam-like structure of the universe had been fully mapped, and confirmed with such careful follow-up work that it helped convince skeptical researchers the underlying picture was correct. Once that reversal took hold, in which galaxies came to be understood as the residue clinging to boundaries rather than the primary content of the universe, a further question naturally followed. If voids make up roughly 4/5 of the total volume of the observable cosmos, and if the largest of them can stretch across hundreds of millions of light years, then what does it actually mean to call any single region of the universe typical? Every observer, wherever they happen to be located, sits somewhere specific, either inside a void, at the edge of one, along a crowded filament, or near the dense core of a cluster. And each of those positions would produce a noticeably different picture of how crowded or how empty the universe appears to be. The cosmological principle, the old assumption of uniformity that shaped a century of theoretical work, still holds up reasonably well when you average across scales large enough to include many voids and many filaments together. At smaller scales, the ones that actually matter for an observer trying to make sense of their own corner of the sky, the principle simply does not apply, and the texture of the universe depends heavily on exactly where you happen to be standing within it. This is not a minor technical footnote. It changes how careful scientists have to be when they use nearby measurements to draw conclusions about the universe as a whole. A measurement of galaxy density taken from inside or near a large void will systematically differ from the same measurement taken from deep inside a dense supercluster, even though both regions belong to the exact same universe, governed by the exact same physical laws. Distinguishing a genuine property of the cosmos from an artifact of our own particular neighborhood has become one of the central challenges facing anyone trying to draw firm conclusions from local observations. And the void near Boötes was one of the first pieces of evidence to make that challenge impossible to ignore. It demonstrated, with a scale and a clarity that could not be dismissed as measurement error, that the universe does not treat every region the same way, and that any single observer's view of the cosmos is filtered, at least in part, by the accident of exactly where their galaxy happens to sit. One of the more difficult questions researchers have tried to answer about the void near Boötes concerns something we cannot see directly at all: the invisible mass called dark matter that appears to outweigh ordinary matter by a wide margin everywhere else in the universe. Ordinary matter, the atoms that make up stars, planets, gas clouds, and every living thing, is relatively easy to track because it emits or absorbs light in ways telescopes can detect. Dark matter does neither. Its presence is inferred entirely through its gravitational effects, through the way it bends light passing near it, and through the way it shapes the rotation of galaxies and the clustering of galaxies into clusters. Inside a normal region of the universe, dark matter is thought to form a kind of invisible scaffolding first, with ordinary matter falling into that scaffolding afterward, gathering along the same filaments and clumping into the same halos that dark matter had already begun to assemble through gravity alone. The obvious question about a region as empty as the void near Boötes is whether the missing galaxies reflect a genuine absence of dark matter, or whether the dark matter is present in something closer to its usual amount, just failing for some reason to gather enough ordinary matter alongside it to form visible galaxies. Answering that question directly is difficult, because the very thing that makes dark matter hard to study anywhere in the universe, its total invisibility to ordinary observation, becomes even harder to work around in a region with almost no galaxies to use as gravitational tracers. Researchers have relied instead on subtle techniques, including the way light from very distant background galaxies gets slightly bent and distorted as it passes near any concentration of mass, whether that mass is visible or not. Early attempts at this kind of measurement across the void near Boötes have been consistent with a genuine reduction in total mass, not just a reduction in visible galaxies, suggesting that whatever suppressed galaxy formation here also left the region short on dark matter itself, not merely short on the ordinary matter that would have lit up as stars. If that interpretation holds, it deepens the puzzle rather than resolving it, because it means the underdensity at the heart of the Boötes void reaches down to the most fundamental scaffolding of cosmic structure, the invisible material that everything else in the universe is built around, and not just the visible galaxies sitting on top of it. Confirming this with the precision researchers would requires exactly the kind of large-scale, high-resolution surveys that have only recently become possible, using instruments capable of measuring the faint gravitational distortion of background light across enormous stretches of otherwise empty sky. And much of that work remains ongoing even now, decades after the void itself was first confirmed to exist. When the first hints of the void appeared in that early survey, the reaction from most of the astronomical community was measured skepticism rather than excitement. Science, especially in a field built on painstaking measurements of extraordinarily faint light, tends to treat surprising results with caution first and enthusiasm only afterward, once the surprising result has survived every attempt to explain it away. There were good reasons for that caution in this case. The original survey had relied on only a handful of narrow fields of view, thin columns of sky rather than a broad sweep. And thin columns are exactly the kind of data that can produce a misleading picture if they happen, by chance, to slice through the edges of ordinary, unremarkable gaps in the galaxy distribution. A modest void that any given patch of universe might reasonably contain could, if a survey happened to cut through it at just the wrong angle, look artificially larger and emptier than it really was, simply because the narrow field of view failed to catch the fainter galaxies scattered around its true edges. There was also the more basic possibility of measurement error. Detecting galaxies at these distances in the early 1980s required working near the very limits of what photographic plates and available telescopes could resolve. And a certain number of faint, genuinely present galaxies could easily have gone undetected simply because they fell below the threshold of what the equipment could pick out from the noise. Any responsible research team faced with a result this surprising had exactly one reasonable path forward, which was to go back and check, using a wider survey, better instruments, and a far larger sample of galaxies, to see whether the apparent gap held up or quietly disappeared once the data improved. That verification effort took years rather than months, partly because measuring the redshift of a single faint galaxy at these distances was, at the time, a slow and painstaking process, requiring long exposures and careful analysis for each individual target, multiplied across hundreds of candidate galaxies scattered through the regions surrounding the original narrow fields. When the expanded survey was finally complete, the result did not soften the original claim. It sharpened it. Where the earlier, narrower survey had suggested an unusual absence of galaxies, the expanded survey, covering a much broader stretch of sky with a much larger sample. Found almost none, where dozens should have appeared if the region had been ordinary. That kind of consistency, a surprising early result, surviving a far more rigorous follow-up rather than dissolving under closer scrutiny, is exactly the pattern that eventually convinces a skeptical scientific community that something genuinely unusual has been found. The void stopped being a tentative claim in a preliminary report and became an accepted, well-documented feature of the observable universe, cited in textbooks and used as a benchmark for testing new theories of how cosmic structure forms. That transition, from surprising anomaly to confirmed cornerstone of modern cosmology, took the better part of a decade to complete, and it stands as a useful reminder of how genuinely strange discoveries usually get established in careful observational science, not through a single striking measurement, but through years of patient, repeated verification that a strange result refuses to go away, no matter how carefully you look for reasons it should. The investigation into this one region of sky has never really stopped, even though the basic discovery is now more than 4 decades old. Newer generations of telescopes and survey programs, built with far more sensitive detectors and capable of measuring far more galaxies across far wider stretches of sky than anything available when the void was first suspected, have continued returning to this same patch of the constellation to refine the picture piece by piece. Wide field surveys conducted from the ground, using digital detectors that can capture the light of hundreds of thousands of galaxies in a single observing campaign, have confirmed and sharpened the original boundaries of the void, tightening the uncertainty around its size and its total galaxy count with each new data release. Space-based observatories designed to map the distribution of galaxies across enormous volumes of the observable universe are expected to extend that picture even further in the coming years, with survey programs specifically built to measure the size, shape, and internal structure of voids as a central part of their scientific goals, rather than as an incidental byproduct of searching for something else. One motivation behind this renewed attention is the connection to the disagreement over how quickly the universe expands, since resolving whether we live inside or near an unusually large underdense region could help settle a debate that has occupied cosmologists for the better part of 2 decades. Another motivation is simply that voids on this scale remain one of the least understood features of the cosmic web, even as the crowded filaments and clusters that occupy the remaining fraction of the universe's volume have been mapped in ever finer detail. It is an odd asymmetry in modern cosmology that the bright, crowded regions of the universe, making up perhaps 1/5 of its total volume, have received the overwhelming majority of detailed observational attention, while the vast, empty majority has often been treated as the space left over once the interesting parts were accounted for. That imbalance is beginning to shift, driven in part by the recognition that voids are not simply empty background, but active, evolving structures that shape the overall expansion of the universe and may carry subtle imprints of conditions from the earliest fractions of a second after the Big Bang. Researchers studying the void near Boötes today are no longer just confirming that it exists, a question settled decades ago beyond reasonable doubt. They are trying to use it as a laboratory, a natural, large-scale experiment in which the balance between gravity and dark energy has already been tested by the universe itself over billions of years, at a scale no experiment on Earth could ever replicate. Every refinement to the count of galaxies along its central filament, every improved measurement of how quickly its boundaries continue to expand, adds another small piece to a much larger puzzle about how the universe organizes itself, and about whether our own galaxy's position within that organization is ordinary or quietly unusual in ways that shape everything we think we understand about the cosmos surrounding us. There is a way of thinking about the thin filament of galaxies running through the center of the void that treats it less as a leftover coincidence and more as a kind of fossil record, a preserved trace of an earlier chapter in the region's history. Before the smaller voids that eventually merged into this one had fully drained of their matter, the boundaries between them would have been slightly denser than the hollow interiors on either side, simply because matter, fleeing each shrinking void, had to pass through those boundaries on its way toward the larger walls further out. As the smaller voids expanded and eventually merged into a single, much larger one, those in between boundaries did not vanish completely. They persisted as a thinner, less pronounced structure, no longer separating anything, but still carrying slightly more galaxies than the surrounding emptiness, because that is where the draining matter had been funneled during the earlier stages of the merger. Millions or billions of years later, that thin structure remains visible as the filament astronomers now observe, a faint scar marking where several smaller voids once met before becoming one enormous void, much the way a geologist might read the layered scars in a rock formation to reconstruct events from long before any human observer existed to witness them directly. This is one of the more elegant aspects of the whole discovery, that a structure, as apparently simple as a hole in the distribution of galaxies, actually encodes a detailed history of its own formation, legible to anyone willing to map its interior carefully enough to notice the pattern. Surrounding the void on every side, meanwhile, is a noticeably denser stretch of the cosmic web, part of the same great network of filaments and walls that extends across the entire observable universe, connecting cluster to cluster in a vast, loosely woven structure sometimes compared to a spider's web stretched across unimaginable distances. These surrounding walls are where the missing galaxies effectively ended up. Matter that might once have gathered inside what became the void, instead drifted outward under the pull of gravity, adding itself to the denser regions at the boundary, thickening the walls even as the interior thinned into the emptiness we observe today. In a sense, nothing was destroyed in the process. Matter was simply redistributed over billions of years, from a region that started out only slightly underdense into an enormous hollow interior, with the difference in mass ending up exactly where you would expect it to end up, concentrated along the crowded boundary rather than spread evenly throughout the volume. Understanding this redistribution in detail has become one of the more productive ways researchers use the void near Bo-Otes to test broader theories of how matter moves and clusters across cosmic time. Since a structure this large, this well-mapped, and this clearly the product of a gradual draining process offers an unusually clean example of gravity's slow, patient work playing out across a stretch of space, large enough to make every step of that process measurable. The void near Bo-Otes was not the last enormous structure astronomers would find once they started mapping the universe in earnest, and placing it alongside its counterparts helps clarify just how unusual, and yet how consistent with a broader pattern, it actually is. On the crowded side of the cosmic web, surveys have identified filaments of galaxies stretching across truly staggering distances, thin structures containing enormous numbers of individual galaxies strung together like beads along a thread that curves across a meaningful fraction of the entire observable universe. These great walls, as researchers often call them, represent the densest examples of the same cosmic web that produces voids at its opposite extreme. Filaments so long and so richly populated with galaxies that they stand as some of the largest coherent structures known to exist anywhere. On the empty side of that same web, several other enormous underdense regions have been proposed or confirmed in the decades since the Bo-Otes discovery, each one adding another data point to the broader question of how large a void the universe is capable of producing, and how often such extreme regions actually occur. Some of these proposed structures remain contested, their boundaries still being refined by ongoing surveys, their exact dimensions shifting slightly with each new data release, as researchers work to separate genuine underdensity from the statistical noise inherent in counting faint, distant galaxies. What all of these structures share, whether crowded filament or hollow void, is that they only became visible once surveys grew ambitious enough to map galaxies across truly vast stretches of sky, rather than the smaller, more manageable fields that earlier generations of astronomers had to rely on. The Boötes void holds a particular place in this broader story because it was among the first structures of this scale to be confirmed with enough rigor to silence most of the early skepticism, making it something of a proving ground for the observational techniques that later revealed the rest of the cosmic web in the detail we now take for granted. Every Great Wall mapped since, every additional void proposed in the years that followed, owes something to the methods first tested and refined, while astronomers were working to confirm that a gap this large, first glimpsed almost by accident in a modest survey, was actually real. To understand why the disagreement over cosmic expansion has become such a stubborn problem, it helps to understand how the nearby measurement is actually made, because the method itself relies on a delicate chain of assumptions that researchers call the cosmic distance ladder. Astronomers cannot simply read the distance to a faraway galaxy off some cosmic ruler. Instead, they rely on objects whose true brightness can be worked out independently, called standard candles, and by comparing that known true brightness to how dim the object actually appears from Earth, they can calculate how far its light has traveled to reach us. Certain kinds of exploding stars, and certain kinds of pulsating stars, whose brightness rises and falls in a pattern tied directly to their true luminosity, serve as the rungs of this ladder, each one calibrated against the rung below it, building outward, step by step from our own cosmic neighborhood to galaxies hundreds of millions of light-years away. Combine these careful distance measurements with the redshift of each galaxy, and you get a direct, local measurement of how quickly the universe is expanding right now in our own corner of the cosmos. The other method skips the distance ladder entirely and instead analyzes the faint patterns imprinted on the ancient background radiation left over from the early universe. Patterns that encode information about the universe's contents and expansion rate at a moment long before any galaxy had formed. Extrapolating that early measurement forward across billions of years, using the standard model of cosmology, produces a second, independent prediction for the expansion rate we should observe today. For years, researchers assumed that any disagreement between these two methods would shrink as measurements improved, since both approaches were expected to converge on the same underlying truth about how quickly the universe is actually expanding. Instead, as instruments grew more precise, the disagreement became sharper rather than softer, eventually reaching a level of statistical significance that made it difficult to dismiss as ordinary measurement error. Researchers have proposed a wide range of explanations, from subtle flaws in the distance ladder itself to genuinely new physics operating in the early universe that the standard model does not yet account for. The possibility that our own galaxy sits inside or near the edge of an unusually large, underdense region offers one of the more conservative explanations on that list, since it does not require inventing any new physics at all. It only requires accepting that the local measurement, the one built on the cosmic distance ladder, has been quietly picking up an extra contribution from the outward pull of a void surrounding our own cosmic neighborhood. A contribution that would not show up in the ancient background radiation measurement, since that method effectively averages over a much larger volume of the universe rather than sampling our own immediate surroundings. Testing this explanation carefully requires exactly the kind of large-scale galaxy surveys that have already proven capable of confirming a void as enormous as the one near Bo-Otez, extended now across an even larger stretch of sky, aimed specifically at measuring whether the region surrounding our own galaxy really is as underdense as the more provocative proposals suggest. The void near Bo-Otez offers something else too, a preview, on a scale we can actually study today, of where the entire universe seems to be heading over unimaginably long stretches of future time. Dark energy, the same pressure that allows a void's interior to expand faster than its crowded surroundings, is not expected to weaken as the universe ages. Every measurement collected so far suggests it behaves like a constant, a fixed property woven into space itself, pushing outward with the same underlying strength, regardless of how much matter happens to be nearby. If that holds true indefinitely, then the imbalance already visible inside regions like the Bo-Otez void will only become more pronounced everywhere else, over timescales that dwarf the current age of the universe by an enormous factor. Galaxies that are gravitationally bound to their neighbors today, held together in groups and clusters by mutual attraction strong enough to resist the overall expansion, will likely remain bound for a very long time to come. But the space between separate groups, the vast gulfs occupied by voids large and small, will keep stretching, slowly carrying isolated groups of galaxies further and further apart from one another until, eventually, most galaxies beyond our own immediate neighborhood recede beyond the reach of any signal we could ever detect. An observer living far enough into that future, inside a galaxy that has already merged with its nearest neighbors and settled into a single, quiet island of stars, would look outward into a sky that had gone almost completely dark of other galaxies, surrounded on every side by exactly the kind of emptiness that fills the interior of the Bo-Otez void today. They would have no way of knowing, just by looking, that their galaxy had ever been part of a richer, more crowded universe, because every trace of that earlier abundance would have expanded permanently out of view long before their own civilization, if one existed, ever developed the tools needed to study the sky. In that sense, the void we are examining now is not simply an unusual, isolated feature of the present-day cosmos. It is closer to a glimpse forward in time, a working demonstration of what large stretches of the universe will eventually look like everywhere, once enough time has passed for dark energy's steady, patient push to overwhelm the pull of gravity across region after region, turning what is today a crowded, structured cosmos into something closer to a collection of isolated islands, drifting apart inside an ever-expanding sea of emptiness. That transformation will take a length of time almost impossible to hold in the mind, far longer than the current age of the universe, but the physics driving it is not speculative. It is the same physics already measurable, right now, inside the boundaries of the void near Bo-Otez, playing out on a scale we can study directly, rather than only calculate from a distance. It is worth asking directly, why a patch of empty sky, confirmed decades ago and consistent in its broad outline with the standard model of cosmology, still manages to unsettle researchers who study it today. Part of the answer has nothing to do with the void itself and everything to do with what it revealed about the limits of an assumption cosmologists had relied on for most of the 20th century. Before this discovery, the working picture of the universe treated any single observer's local surroundings as a fair sample of the whole, a small patch of cosmic average that could be trusted to represent conditions almost anywhere else. The Bo-Otez void demonstrated, with a scale too large to explain away, that this assumption breaks down at exactly the scales that matter most for anyone trying to draw conclusions from their own corner of the sky. A region hundreds of millions of light-years across, missing the overwhelming majority of the galaxies it should have contained, is not a minor exception to the rule of cosmic averages. It is a demonstration that entire stretches of the universe can differ dramatically from the average, persist that way across billions of years, and only reveal themselves once a survey happens to look in exactly the right direction, with enough patience and precision to notice. That realization carries an uncomfortable implication that follows the discovery wherever it goes. If a gap this size can exist, quietly, until a particular team of astronomers happen to point their instruments at exactly the right patch of sky in exactly the right year, then how much of the broader universe remains similarly unmapped, similarly capable of surprising us the moment someone finally looks closely enough? Every confirmed void adds to a growing sense that the universe is less uniform, less predictable at intermediate scales, and less thoroughly understood than the tidy equations of the standard cosmological model might suggest at first glance. None of this means the standard model is wrong. It has passed test after test across decades of increasingly precise observation, and it remains the best framework available for understanding how the universe evolved from its earliest moments to the structure we observe today. What the void near Boötes represents is a reminder that passing a test is not the same as fully explaining every detail of what that test reveals. The model can accommodate a void this size. It cannot yet tell you, with confidence, why this particular region of space became this particular kind of empty, or how many similarly extreme surprises remain hidden in stretches of the sky that no survey has yet examined closely enough to notice. That open, unresolved edge, sitting quietly at the boundary of an otherwise well-tested theory, is the real reason researchers keep returning to this one patch of sky, long after the initial thrill of discovery faded into the routine business of ordinary science. Turn the lens back toward our own galaxy for a moment, because the story of enormous cosmic emptiness is not only something happening far away near a distant constellation. Our own Milky Way sits at the edge of a modest, underdense region, far smaller than the void near Boötes, but a genuine gap in the cosmic web nonetheless, with the richer, more densely populated stretches of the universe lying mostly in one general direction rather than surrounding us evenly on all sides. Beyond that immediate gap sits a much busier neighborhood, home to enormous gatherings of galaxies whose combined gravity is slowly pulling our entire local group, along with many of our nearest galactic neighbors, across millions of light-years toward a distant concentration of mass, sometimes described only half-jokingly as an attractor, because its full extent and exact nature remain difficult to observe directly, hidden as it partly is behind the crowded plane of our own galaxy. Meanwhile, our nearest large neighbor, the great spiral galaxy visible on a clear night as a faint smudge, is slowly closing the distance between itself and our own, drawn inward by mutual gravity rather than pushed apart by the overall expansion that governs more distant, unbound galaxies. Over an extraordinarily long stretch of future time, these two galaxies are expected to merge into a single, larger galaxy, a slow, gentle collision stretched across billions of years rather than any sudden, violent event, reshaping both galaxies into something new while leaving most of their individual stars and any surviving planetary systems largely undisturbed by the process. Once that merger completes, the resulting galaxy is likely to find itself increasingly alone, as smaller neighboring groups drift beyond the reach of any signal we could detect, carried away by the same steady cosmic expansion that has already carved enormous, permanent gaps like the one near Boötes into the fabric of the universe elsewhere. Whether that eventual isolation counts as evidence that our own neighborhood is quietly evolving towards something resembling a modest void of its own, or whether it simply reflects the ordinary fate awaiting nearly every galaxy group given enough time, is difficult to say with confidence from where we currently stand. What is clear is that the same forces responsible for the enormous emptiness near Bo-Otes are already at work, slowly and patiently, within our own cosmic backyard, reshaping the distances between us and our neighbors on timescales too long for any single human lifetime to notice directly, but well within reach of the careful measurements astronomers have learned to make across the small fraction of cosmic history our species has so far been able to observe. Before settling on the picture of a genuine, physical void, researchers had to work through a long list of more mundane explanations, because extraordinary claims about the structure of the universe demand that every ordinary possibility be exhausted first. One early concern involved dust, both within our own galaxy and scattered through intergalactic space, since a sufficiently thick screen of dust sitting between Earth and a distant patch of sky could dim faint galaxies enough to make them effectively undetectable, creating the illusion of a gap where galaxies were actually present but simply too faint to register. Careful mapping of dust within our own galaxy showed no unusual concentration in the direction of the void, and measurements of background objects seen through the region showed no evidence of the kind of dimming or reddening that a thick dust screen would produce, effectively ruling out that explanation. A second concern involves selection effects buried in how the original survey had chosen which galaxies to examine in the first place, since any survey that favors brighter, more easily detected galaxies over fainter ones can produce misleading gaps if an entire population of faint galaxies happens to cluster at a particular distance. Follow-up surveys address this concern directly by pushing detection thresholds fainter and by using different telescopes and different detection methods entirely. Methods with different strengths and different blind spots than the original survey, and the gap persisted regardless of which method was used to search for it. A third possibility, more subtle than the first two, involved the chance that the original narrow fields of view had simply been unlucky, happening to align with the thin walls of several separate, more modest voids in a way that created the illusion of one single, enormous gap where several smaller, more ordinary ones actually existed side by side. This concern turned out to be closer to correct than the other alternatives, though not in the way early skeptics expected, since the merger explanation that eventually emerged does involve several smaller voids, but confirms that they genuinely did coalesce into one continuous, physically connected region, rather than remaining separate and merely appearing connected due to an unlucky alignment of the original survey fields. Each of these alternative explanations required real observational work to rule out, work that took years and multiple independent teams using different instruments and different techniques, and the fact that the void survived every one of these tests is precisely what elevated it from an interesting anomaly to one of the most thoroughly confirmed structures in modern cosmology. Science rarely accepts a surprising result on the strength of a single measurement, and the Bo-Otes void stands as a useful example of how a genuinely strange discovery earns its place in the accepted record of the universe. Not through a single dramatic announcement, but through a long, patient process of trying every reasonable way to make the surprising result disappear, and finding, each time, that it refuses to go away. Part of why this single patch of sky has been revisited so many times over the past several decades has to do with how dramatically the tools available to astronomers have changed since the original discovery. The earliest survey relied on photographic plates, sheets of light, sensitive material exposed for long stretches of time at the focus of a telescope, then developed and examined by eye or with early mechanical measuring devices to identify faint smudges of light corresponding to distant galaxies. The process was slow, labor-intensive, and limited by how much light a photographic plate could actually register before the image saturated or the faint signal was lost in the background noise of the night sky itself. Digital detectors, developed and refined through the final decades of the 20th century, changed this picture entirely, allowing astronomers to record far fainter light with far greater precision and to process enormous volumes of data automatically rather than examining each photographic plate by eye. Wide-field digital surveys conducted from the ground eventually made it possible to measure the positions and redshifts of hundreds of thousands, and eventually millions, of galaxies across large stretches of sky, in a fraction of the time the original 1981 survey had required to examine just a handful of narrow fields. Each new generation of instruments allowed researchers to revisit the void near Beau-Otes with greater confidence, refining its boundaries, improving the count of galaxies along its central filament, and testing the merger explanation against increasingly detailed data. Space-based observatories, free from the blurring effects of Earth's atmosphere, added another layer of precision, allowing extremely faint and distant background objects to be measured clearly enough to detect the subtle gravitational distortions that hint at the presence of otherwise invisible dark matter within the void. None of this technological progress has overturned the basic picture established by that original, modest survey conducted with instruments that would look primitive by modern standards. It has instead confirmed and sharpened that original result again and again, a reminder that a genuinely careful measurement, even one made with comparatively limited equipment, can hold up remarkably well against decades of far more sophisticated scrutiny, provided the original researchers approached the strange result with the same caution and rigor that later generations would eventually bring to testing it. Return, for a moment, to the question of what chemistry might look like inside one of the few galaxies scattered along the void's central filament, because the isolation that defines this region would shape more than just the night sky an observer there might see. Heavy elements, the building blocks of rocky planets and of life as we understand it, are manufactured almost entirely inside stars, forged through nuclear fusion over a star's lifetime, and then scattered outward when that star eventually reaches the end of its life, enriching the surrounding gas cloud with material that later generations of stars and the planets that form around them can draw upon. A galaxy that has spent its entire history relatively isolated, without the frequent, close encounters and occasional mergers that stir up star formation in more crowded regions of the cosmic web, tends to build up its supply of heavy elements more gradually, since each new burst of enriched material depends on the previous generation of stars having already lived out their full lifespans undisturbed. This slower enrichment does not necessarily prevent rocky planets from forming inside a void galaxy. It simply means those planets may take longer to appear, and the earliest generations of planets to form around the earliest stars in such a galaxy are more likely to be dominated by lighter elements, closer in composition to gas giants than to worlds with solid, rocky surfaces. Given enough time, even an isolated galaxy accumulates heavy elements at a meaningful rate. Since stars continue forming and reaching the ends of their lives, regardless of how crowded or empty the surrounding universe happens to be, and the slower pace inside a void simply stretches this process across a longer stretch of cosmic history rather than preventing it outright. There is a second consideration worth holding alongside the first, concerning how life, once it emerges somewhere, might spread from one world to another. Some researchers have proposed that simple biological material could, in principle, survive being ejected from one planetary system and eventually seed the beginnings of life on another, carried across interstellar distances by chance collisions and the slow drift of debris through space. Inside a crowded region of the cosmic web, with many stars and planetary systems packed relatively close together, such transfers, however rare, remain at least conceivable across sufficiently long timescales. Inside the vast, isolated stretches of a void, with individual galaxies separated by distances so large that light itself needs hundreds of millions of years to cross the gap between them. Any such transfer becomes almost impossible to imagine, leaving each isolated pocket of potential biology, if it exists at all, to develop entirely on its own, without any realistic chance of contact or exchange with whatever might be happening in a neighboring galaxy across the same enormous gap. Whether this isolation makes life more resilient, forced to develop independently and perhaps more robustly, without reliance on outside contribution, or simply rarer, denied the additional opportunities that a more crowded neighborhood might provide, remains an open question. One more thread in the broader puzzle. This single patch of empty sky continues to raise for anyone willing to think carefully about what its emptiness actually implies. There is something genuinely unusual about treating an absence as a subject of careful scientific study in its own right, rather than simply noting it and moving on to whatever brighter, more obviously interesting object happens to sit nearby. Most of astronomy, for understandable reasons, concerns itself with things that emit light, since light is the primary channel through which we learn almost everything we know about the universe beyond our own solar system. Stars shine. Galaxies glow with the combined light of billions of stars. Even black holes, which emit no light of their own, betray their presence through the glowing material spiraling into them, or through the way they bend and distort the light of objects passing behind them. A void offers none of this. There is nothing to point a telescope at directly, no glowing target sitting conveniently in the center of the emptiness, waiting to be photographed and analyzed. The only way to study a void at all is to study everything around it, to carefully map what exists at its boundaries, to measure how sparse the handful of objects within it happen to be, and to infer, from that pattern of absence, the full extent and character of something that offers no direct signal of its own. This makes voids, and the Boötes void especially, a strange kind of scientific subject, one defined entirely by what is missing rather than by what is present. And yet that absence turns out to carry an enormous amount of information once researchers learned how to read it properly. The size, shape, and internal structure of a void encodes details about the earliest moments of the universe, about how gravity and dark energy compete against each other on the largest observable scales, and about how representative or unrepresentative any single observer's local neighborhood might be compared to the universe as a whole. Nothing, in this context, is not the opposite of data. It is a particular, information-rich kind of data, one that took astronomers the better part of a century to learn how to recognize, measure, and interpret with the same rigor traditionally reserved for the bright, obvious objects that first drew human attention to the night sky. The void near Boötes stands as one of the clearest demonstrations of that lesson, a stretch of space defined by what it lacks, and precisely because of that lack, one of the more scientifically productive regions of sky that astronomers have ever chosen to study in detail. There is a particular kind of paradox buried in the story of how this void came to be known at all, worth sitting with for a moment before moving toward a close. Structures that are unusually dense tend to announce themselves. A cluster containing an unusual concentration of galaxies shows up as a bright, obvious clump the moment a survey passes over it. Impossible to miss, even with fairly modest equipment, because more galaxies simply means more light gathered into one place. A structure defined by unusual emptiness works in exactly the opposite way. And that difference turns out to matter enormously for how long something this large can go unnoticed. An underdense region does not announce itself. It simply fails to produce the signal that a survey is looking for, which means detecting it requires first establishing, with real confidence, what an ordinary, unremarkable patch of sky should look like, so that the absence of that ordinary pattern can be recognized as meaningful rather than dismissed as an unremarkable gap in an incomplete dataset. This is part of why an underdense region on this scale could persist, undetected, for the entire history of astronomy, up until a modest survey in the early 1980s finally happened to look in the right direction with the right method to notice it. Human perception, and by extension the instruments early astronomers built to extend that perception, evolved to notice presence far more readily than absence. We are built to spot the unexpected object in a scene, the sudden movement, the bright flash against a dark background, not the quiet failure of something to appear where our expectations said it should. Learning to treat an absence as seriously as a presence, to measure emptiness with the same rigor traditionally reserved for measuring light, required astronomers to develop an entirely different way of thinking about what counts as a discovery in the first place. The void near Boötes helped establish that different way of thinking, demonstrating that some of the most important structures in the universe are defined not by what they contain, but by what they conspicuously, measurably, and enormously lack, and that learning to notice and study that lack properly opened an entirely new chapter in how astronomers understand the shape of the cosmos surrounding us. The proposal that our own galaxy might sit near the center of an enormous underdense region did not emerge from a single measurement or a single research team working in isolation. It grew out of a series of galaxy-counting surveys conducted over roughly a decade, each one extending the sampled volume of space a little further outward from Earth. Each one refining the statistical methods used to compare local galaxy density against the average density expected across the universe as a whole. The researchers behind the proposal were careful, from the beginning, to frame their result as a hypothesis requiring further testing rather than a settled fact. Aware that a claim this significant, suggesting our own galaxy occupies an unusual rather than typical position in the cosmos, would face exactly the kind of scrutiny that any extraordinary result deserves. That scrutiny arrived promptly, and it continues today. Some independent surveys, using different methods and different samples of galaxies, have reported findings broadly consistent with an underdense region surrounding our local neighborhood, lending support to the original proposal. Others have reported a weaker effect, or have questioned whether certain systematic biases in how galaxies are selected and counted might be partially responsible for the apparent underdensity, rather than a genuine physical gap in the distribution of matter. One researcher who has continued pursuing this question in detail, publishing refined analyses across several years, has argued that the evidence for a genuine local underdensity remains strong, and that its existence offers a natural, relatively conservative explanation for part of the ongoing disagreement over how quickly the universe is expanding. Critics of the proposal have countered that invoking a special, underdense region surrounding our own galaxy uncomfortably resembles exactly the kind of assumption that the cosmological principle was designed to avoid, since it implies our own location carries some genuine significance rather than being an entirely unremarkable sample of the wider cosmos. The debate remains unresolved, sitting exactly at the intersection of two ideas this discussion has already introduced: the confirmed reality of enormous voids like the one near Boötes, and the open question of just how representative any single observer's neighborhood actually is compared to the universe taken as a whole. Resolving it fully will likely require the kind of wide, deep galaxy surveys currently being planned and, in some cases, already underway, extending the sampled volume of space around our own galaxy far enough to settle, with real statistical confidence, whether the underdensity researchers have proposed is a genuine feature of our cosmic neighborhood or an artifact of the particular methods used to measure it. The unusually cold patch found in the ancient background radiation has remained a subject of active investigation long after it was first noticed, precisely because confirming its cause would tie together several separate threads of this discussion into a single, coherent picture. If the cold patch really is caused by ancient light losing a small amount of energy while passing through an enormous void, then the region of sky containing that cold patch should also show a genuine deficit of galaxies detectable through ordinary redshift surveys conducted independently of any measurement of the background radiation itself. Several survey teams have pursued exactly this test, mapping galaxy density across the region of sky associated with the cold patch and comparing it against the average density found elsewhere. Some of these surveys have reported a modest underdensity in roughly the expected location, lending support to the void-based explanation. Others have found the effect weaker than a void, large enough to fully explain the cold patch would require, suggesting that some combination of a genuine, if more modest, void together with an additional, still unidentified contribution might be needed to account for the full size of the anomaly. This kind of partial, incomplete confirmation is common in observational cosmology, where a single proposed explanation rarely accounts for every detail of a complex signal on the first attempt, and where researchers often spend years refining both the observational technique and the underlying theoretical model before a clean, fully satisfying picture finally emerges. What matters for this discussion is that the entire line of investigation depends on having already established, beyond reasonable doubt, that voids on an enormous scale genuinely exist and genuinely leave measurable imprints on the light passing through them. Without the earlier confirmation of the void near Boötes, proposing that an unusual cold patch in the ancient background radiation might be caused by a similarly enormous void elsewhere in the sky would have sounded far more speculative than it does today. Instead, that earlier confirmation gave researchers a template, a working example of exactly how large, how empty, and how measurable a void could genuinely be, making the void-based explanation for the cold patch a serious, testable hypothesis, rather than an exotic long shot proposed only because more conventional explanations had already failed. There is a particular kind of vertigo that comes from trying to hold the true scale of this structure in your mind for more than a few seconds at a time. Every measurement discussed so far, the diameter spanning hundreds of millions of light years, the handful of galaxies scattered where thousands should exist, the billions of years the void has spent slowly draining and merging into its current shape, describes something that no human sense was ever built to perceive directly. We evolved to judge distance by the time it takes to walk somewhere, to judge scale by comparing objects to our own bodies, to judge emptiness by glancing across a room or a valley and noticing what is missing from it. None of those instincts transfer usefully to a structure that light itself needs hundreds of millions of years to cross. And yet the void is not an abstraction. It is a real, physical region of the actual universe we live in, sitting at a specific set of coordinates, casting a specific, measurable shadow on the ancient light passing near it, containing a specific, accountable number of galaxies arranged along a specific filament that astronomers have mapped in genuine detail. The gap between how real this structure is and how impossible it remains to intuitively grasp is, in some sense, the entire point of studying it at all. Confronting a structure this large forces a kind of humility that smaller, more human-scaled discoveries rarely demand, a recognition that the universe operates comfortably on scales our minds were never designed to hold, and that understanding those scales requires leaning on careful measurement and patient mathematics, rather than on the kind of direct, intuitive grasp we bring to more ordinary experiences. That humility is not a failure of human understanding. It is closer to the appropriate response to genuinely encountering something this vast, an acknowledgement that the tools of careful science, redshift surveys, background radiation maps, gravitational lensing measurements, can reach places our raw intuition never could, revealing structures like this one that would otherwise have remained permanently invisible, hidden in plain sight within a patch of sky that, to the naked eye, looks no different from any other quiet, unremarkable stretch of stars. Much of what researchers know about how a region like this could form comes not from direct observation alone, but from an entirely different kind of tool: large computer simulations that model the gravitational interaction of an enormous number of individual mass points across simulated billions of years. These simulations begin from a simplified version of the early universe, seeded with tiny density variations, matching those measured in the ancient background radiation, and then let gravity run its course, calculating how each simulated clump of mass pulls on every other clump across the simulated volume, generation after generation, until the simulated universe develops a structure that can be compared directly against what real telescopes actually observe. When researchers run these simulations with enough resolution and across a large enough simulated volume, the resulting structure consistently develops the same basic foam-like pattern found in the real universe. Dense filaments and clusters separated by hollow, underdense regions of varying size. Voids comparable in scale to the one near Boötes do appear in these simulations, though not in every run, and not with predictable timing or location, emerging instead as one possible outcome among many, shaped by the particular random arrangement of density variations fed into that specific simulation at the start. This gives researchers a useful, if imperfect, way of testing whether the void we observe is consistent with the standard model of cosmology, or whether its existence points towards some missing ingredient the model has not yet accounted for. So far, the void has passed this test reasonably well. Simulations built using the standard model, without any exotic additions, do produce structures of comparable scale often enough that researchers consider the void an unusual but not impossible outcome. Exactly the kind of rare event that a universe this large, containing an enormous number of independent regions where structure could form differently, should be expected to produce somewhere, purely as a matter of statistics. The honest limitation of this approach is that it can only ever offer a statement about probability rather than a specific, causal explanation. A simulation can show that a void this size should appear somewhere across a sufficiently large simulated volume. It cannot point to this exact region of the real sky and explain why the specific pattern of density variations present in the actual early universe happen to produce a void in this particular direction, rather than in one of the countless other directions where a similarly rare underdensity might just as easily have formed instead. Beyond testing the standard picture of dark energy and structure formation, voids like the one near Boötes have also become an unexpected testing ground for an entirely different category of theory: Proposals that attempt to explain cosmic acceleration not through some new form of energy, but through a modification of gravity itself at the largest scales. Standard gravity, the same theory that accurately describes the orbit of planets and the bending of starlight near massive objects, has been tested with extraordinary precision within our own solar system and around individual stars. Whether that same theory continues to hold exactly, without any modification, across distances measured in hundreds of millions of light-years is a genuinely open question, and voids offer one of the cleanest possible environments to check. Because a void contains so little matter, any modification to gravity that depends on the local density of mass nearby, becoming more noticeable in emptier surroundings and less noticeable in denser ones, would be expected to show its clearest effects precisely inside a region like this one, where ordinary matter is scarce enough that any such modification would not be masked by the much stronger, conventional gravitational pull found in crowded clusters. Researchers have used careful measurements of how galaxies move near the boundary of large voids, comparing the observed motion against what standard gravity combined with dark energy would predict, to place limits on how large any such modification could plausibly be. So far, these tests have not turned up convincing evidence that gravity behaves differently inside a void than the standard theory predicts, which supports the conventional explanation involving dark energy overwhelming a weak gravitational pull, rather than gravity itself changing its behavior in emptier surroundings. But the tests continue, refined with each new generation of survey data, because a region this large, this empty, and this precisely mapped remains one of the very few places in the observable universe where such a subtle and fundamental question can actually be investigated with any real hope of a conclusive answer. If you were to step outside on a clear night and locate the constellation that gave this void its name, you would not need any special equipment to find your starting point. Boötes is easy to pick out, largely because of the bright orange-tinted star anchoring one end of its kite-shaped outline, a star called Arcturus, one of the brightest points of light visible in the night sky from much of the northern hemisphere. Arcturus itself is an aging star, swollen far larger than our own Sun as it has moved through the later stages of its life, and it sits close enough to Earth, in cosmic terms, that its light reaches us in only a few decades, rather than millions or billions of years. Nothing about Arcturus, or about the modest scattering of fainter stars surrounding it that make up the rest of the constellation, hints at what lies far beyond them. Every star visible in that patch of sky belongs to our own galaxy, close by any cosmic measure, while the void itself sits enormously farther away, well beyond any star an unaided eye could ever hope to detect directly. Looking toward Boötes on an ordinary night, there is no visual clue at all that you are gazing, indirectly, in the general direction of one of the largest confirmed empty regions in the observable universe. The stars in the foreground simply happen to occupy the same general direction as a structure so distant, so faint, and so fundamentally different in scale that it takes sensitive instruments and careful redshift surveys, rather than the naked eye, to reveal it at all. This gap between what a casual glance at the night sky reveals and what careful measurement eventually uncovers is, in many ways, the whole story of this discovery in miniature. The universe does not announce its stranger features to a casual observer. It reveals them only when someone takes the trouble to measure it patiently enough and carefully enough to notice that something ordinary looking on the surface conceals, further out, an emptiness large enough to reshape how an entire field of science understands the structure of everything surrounding us. There is a broader lesson embedded in this discovery that extends well beyond the specific physics of voids and cosmic structure, one that touches on how scientific progress actually tends to happen in practice. The most celebrated moments in the history of astronomy usually involve finding something, a new planet, a new kind of star, a signal from a previously unknown object glowing somewhere in the depths of space. Finding nothing, by contrast, rarely makes for an obviously exciting headline, and for a long stretch of the 20th century, an unexpected gap in a galaxy survey might easily have been treated as a disappointing null result, worth a brief mention in a technical paper, before researchers moved on to searching for something more conventionally interesting. What makes this particular gap different is that the researchers who found it took the absence itself seriously, treating a failure to detect galaxies with the same rigor and follow-up effort that a genuine detection would have received. That decision, to chase down an absence with the same discipline normally reserved for chasing down a presence, is what eventually turned a modest anomaly in an early survey into one of the most thoroughly confirmed and scientifically productive structures in modern cosmology. It is worth remembering, when new surveys turn up their own unexpected gaps in the years ahead, that the most significant discovery hiding in a dataset is not always the bright, obvious signal sitting at the center of attention. Sometimes it is the quiet, easily dismissed absence at the edge of the frame, waiting for someone patient enough to ask why it is there at all, and stubborn enough to keep asking until a satisfying answer, or at least a well-confirmed and carefully measured mystery, finally emerges. The handful of galaxies that do exist inside the void turn out to differ in character, not just in number, from galaxies found in more crowded parts of the universe, and that difference offers another useful clue about how environment shapes the way a galaxy grows and changes over cosmic time. Galaxies embedded in dense clusters experience frequent gravitational encounters with their neighbors, encounters that can strip away the gas needed to form new stars, trigger sudden bursts of star formation, or gradually reshape a once orderly spiral into a smoother, more rounded elliptical form over billions of years. Galaxies isolated deep inside a void experience almost none of this disruption. Left largely undisturbed by close neighbors, they tend to hold on to their gas for longer, continuing to form new stars at a steady pace rather than exhausting their fuel in occasional dramatic bursts triggered by a passing companion. Surveys of galaxies inside large voids, including the handful scattered along the filament running through the center of the region near Bo-Otes, have generally found a higher proportion of actively star-forming, spiral-shaped galaxies compared to the mix typically found in dense clusters, where smoother, quieter, elliptical galaxies with little ongoing star formation tend to dominate instead. This pattern supports a broader idea in modern astronomy, sometimes summarized as the observation that a galaxy's surroundings shape its evolution nearly as much as its own internal properties do. Two galaxies that began with similar mass and similar initial composition can end up looking quite different billions of years later, purely because one happened to form inside a crowded cluster, subject to constant gravitational disruption, while the other happened to form in isolation, quietly continuing to build new stars undisturbed for the better part of cosmic history. The void near Bo-Otes, precisely because its galaxies have been left so thoroughly alone, offers researchers a useful extreme case for testing this idea, a natural control group of sorts, showing what galaxy evolution looks like when almost none of the disruptive influences common elsewhere in the universe are present to interfere with it. It is easy, looking back from the present, to forget how recent this whole picture of a foam-like universe, riddled with enormous hollow regions, actually is in the long history of astronomy. Anyone who studied the structure of the cosmos before the final decades of the 20th century would have learned a picture built almost entirely around the cosmological principle a universe assumed to be smooth and evenly filled once you looked past the relatively modest clumping of individual galaxies into small groups and clusters. Students studying cosmology today learn something quite different from the outset. A universe organized into a genuine cosmic web, with galaxies concentrated onto thin, sheet-like structures and enormous, well-documented voids occupying most of the available volume in between. The void near Boötes played a meaningful part in that shift, serving for years as one of the standard, textbook examples used to introduce the very concept of a cosmic void to new generations of students, precisely because it was large enough to be unmistakable, well enough confirmed to avoid any lingering controversy over whether it was genuinely real, and well enough studied to support a detailed discussion of how such a structure could plausibly have formed. That teaching role matters beyond the classroom, because the concepts a field chooses to feature prominently in its introductory material tend to shape how an entire generation of future researchers instinctively thinks about the subject. A student who learns from the outset that voids are common, enormous, and central to the structure of the universe approaches new observations with a different set of expectations than a student trained under the older assumption of rough cosmic uniformity. More inclined to ask what an unexpected gap in a new data set might reveal, rather than dismissing it immediately as an artifact or an error. In that quiet way, a single confirmed structure, first glimpsed almost by accident in a modest survey more than 4 decades ago, has continued to shape how astronomers approach entirely new questions today. Long after the original discovery itself faded from active headlines and settled instead into the accepted, foundational background of how modern cosmology understands the universe. One more thread deserves attention before drawing these ideas together, concerning how researchers actually distinguish a genuine cosmic void from an ordinary, unremarkable gap that any survey of galaxies will always contain simply due to the uneven, clumpy nature of matter at smaller scales. Not every stretch of empty-seeming sky qualifies as a void in the scientific sense. The space between individual galaxies within an otherwise ordinary cluster is technically empty too, but nobody treats that ordinary spacing as evidence of some deep cosmic mystery, because it falls well within the range of clumping any reasonable model of structure formation predicts. Astronomers define a genuine void using a specific statistical threshold, typically requiring that the density of matter within a candidate region fall to a small fraction of the average cosmic density, sustained consistently across a large enough volume that ordinary statistical fluctuation cannot easily explain it away. Meeting that threshold requires more than simply noticing a patch of sky with fewer galaxies than its neighbors. It requires careful modeling of exactly how much variation ordinary random clumping should produce on its own, so that a genuine underdensity can be distinguished with confidence from an unremarkable, expected gap that any survey of a clumpy universe will inevitably contain here and there. The void near Boötes cleared this threshold by an enormous margin, which is part of why it became such an influential example once its existence was confirmed. Where a modest, ordinary gap might show a density perhaps half of the surrounding average, well within the range normal clumping easily produces, the region near Boötes showed a density reduced to a small fraction of that average, sustained across a volume so large that no reasonable model of ordinary statistical clumping could account for it. This distinction matters for understanding why some proposed voids remain controversial, while others, like this one, are treated as fully established. A candidate void identified in a smaller, less thoroughly sampled survey might show promising early hints of underdensity that later, More careful analysis reveals to be within the range ordinary clumping could produce, dissolving the apparent discovery once better data becomes available. The void near Boötes never dissolved under this kind of scrutiny. No matter how many times researchers returned with improved instruments and larger samples, which is precisely the pattern that separates a genuine, deeply significant structure from an artifact of incomplete early data. Understanding this distinction also clarifies why astronomers continue debating the reality and extent of some other proposed underdense regions, including the much larger local underdensity some researchers believe surrounds our own galaxy. Since establishing that kind of claim with the same level of confidence achieved for the region near Boötes requires exactly the same rigorous statistical threshold, applied across a survey wide and deep enough to rule out ordinary clumping as a complete explanation, a bar that some of the more ambitious recent proposals have not yet fully cleared to the satisfaction of every skeptical researcher in the field. It is worth pausing on one more idea that ties several earlier threads together: the question of how researchers actually decide how much attention a single confirmed structure deserves relative to everything else competing for study time and telescope resources across the wider field of astronomy. Every year, observatories receive far more proposed research projects than they have time to support, forcing careful decisions about which questions deserve the scarce hours available on the world's most sensitive instruments. A structure that had turned out to be a simple measurement error, quietly corrected once better data arrived, would have disappeared from that competition for attention almost immediately, absorbed back into the ordinary business of routine galaxy surveys. The void near Boötes took the opposite path, earning renewed observational attention again and again across 4 decades, precisely because each new investigation kept confirming, and often refining, rather than overturning, the basic picture established by that first uncertain survey. This pattern, in which a discovery earns increasing rather than diminishing attention over time, is itself a meaningful signal within the scientific community, a sign that a result has moved from curiosity to genuine cornerstone, the kind of structure other theories get tested against, rather than a detail waiting to be explained away. Researchers proposing new models of cosmic structure formation routinely check whether their models can reproduce a void of this scale and this internal structure, using it as a benchmark, the way engineers might use a well-characterized reference material to calibrate a new instrument. If a proposed model cannot produce anything resembling the void near Boötes given realistic initial conditions, that failure counts meaningfully against the model, precisely because this particular void has been measured carefully enough and confirmed thoroughly enough that its basic properties are no longer seriously in doubt. Few discoveries in observational astronomy earn this kind of enduring role as a benchmark, and the ones that do tend to share a common thread with the story told here: an initially surprising, almost accidental observation, followed by years of patient, rigorous verification that transformed a tentative claim into a foundational piece of how an entire field understands the universe it is trying to describe. Return, one last time, to that original moment. An astronomer in 1981, staring at a chart of galaxy positions, noticing a stretch of sky that refused to contain what it should have contained. At the time, there was no way to know whether that gap represented a genuine discovery or a simple mistake, a limitation of the equipment, an unlucky alignment of a narrow survey field, or a real, physical structure large enough to reshape how an entire field understood the universe. It took years of patient follow-up work to settle the question, expanding the survey, ruling out dust, ruling out selection bias, testing the result against instrument after instrument, before the gap could finally be accepted as real beyond reasonable doubt. What emerged from that patient work was not simply a curiosity, an unusual gap tucked away in one corner of the sky, but a genuine turning point in how scientists picture the cosmos at the largest scales. The universe, it turned out, is not a smooth, evenly filled expanse dotted here and there with galaxies. It is closer to a vast, foam-like structure, thin walls and filaments of matter stretched across enormous hollow interiors, with galaxies occupying only a small fraction of the total available volume, while emptiness claims the overwhelming majority of it. The void near Boötes remains one of the clearest, most thoroughly measured examples of that hollow interior, a region spanning hundreds of millions of light-years, holding only a scattered handful of galaxies where thousands should exist, still slowly growing, still slowly draining what little matter remains inside it, outward toward the denser walls at its boundary. Its existence forced a reconsideration of an assumption cosmologists had relied on for most of the 20th century: the idea that any single observer's local neighborhood fairly represents conditions across the wider universe. It offered a natural laboratory for testing the balance between gravity and dark energy, at scales no experiment on Earth could ever replicate. It left a measurable imprint on the oldest light in the universe, and it helped researchers take seriously the possibility that our own galaxy might sit near the edge of a similarly, if more modestly, underdense region, with consequences that reach all the way into one of the most contested open problems in modern physics: the disagreement over how quickly the universe is actually expanding. And after 4 decades of careful investigation, the deepest question the void first raised remains only partly answered. Researchers understand, in broad outline, how a region this large could have grown through the slow merger of several smaller underdense regions over billions of years of patient gravitational sorting. They still cannot fully explain why this particular patch of the early universe, out of the countless directions the sky offers, happened to tip towards such extraordinary emptiness in the first place. That open question is, in its own way, the most honest place to leave this story, because it captures something true about how science actually works at its edges. Confirmation is not the same as complete understanding. A structure can be measured with extraordinary precision, tested against every reasonable alternative explanation, and still leave its deepest why only partly answered, waiting for whatever future survey or future theory finally closes the gap between what we can confirm and what we can fully explain. Until then, the void near Boötes sits quietly where it has always sat, hundreds of millions of light-years away, behind the familiar stars of an easily recognized constellation, continuing its slow, patient expansion, indifferent to whether anyone on a small rocky planet happens to be looking in its direction or thinking about what its emptiness actually means. If you have made it this far, be sure to like this video and subscribe for more journeys into the strange, quiet corners of the cosmos. Now, take a deep breath, and remember that even nothing, studied carefully enough, has a story worth telling.